This is the first video from Chapter 17, the chapter of additional aspects of aqueous equilibrium, and this video is going to talk about strong acid and strong base titrations. So backing up a second, Chapter 17 is just a continuation of Chapter 16, and in Chapter 16 we learned how to handle strong acids to calculate their pH, strong bases to calculate their pH, weak acids to calculate the pH, and weak bases to calculate their pH. At the beginning of Chapter 17, we also looked at what happens if you mix a weak acid and a weak base together. So Chapter 16 was all about, okay, there's one chemical. Calculate the pH of that one chemical. Chapter 17 is all about, hey, let's do two chemicals. Let's mix two chemicals together and calculate their pH. So in Chapter 17, you're going to see the word titration a lot because that's usually when we're mixing an acid and a base together. Typically, that's what we're doing. So because of all these combinations that are going to happen, I've made a lovely little handout, which if I had been thinking, I would have printed and given you the last time we had class, but instead you can find this in Canvas in the Chapter 17 thing. Sorry, I'm going to back out. I'm going to get to right here. This is the table that I made. It's just kind of a helpful hint. So in Chapter 16, every time we read a question, the first thing I wanted you to do was identify the chemical as either a strong acid, a strong base, a weak acid, or a weak base. And I'm going to add a fifth thing to that list, which is something that's neutral. So in Chapter 17, we're going to continue doing that. You read a question, you're going to look at every chemical and identify it as one of those things. So it's just in Chapter 17, there's going to be two chemicals in every question instead of one. So this table is just a reminder or a helpful hint on once you identify what the chemicals are, you can look at this chart to figure out what to do. 5 of the boxes on this we've already talked about. So the box that says weak acid only, we learned that in Chapter 16. That's to do an ice table from the HA equation. Weak bases only, that's also from Chapter 16. It's to do an ice table from the B plus water equation. Weak acid and weak base, we learned that at the beginning of Chapter 17. That was if we have a weak acid and a weak base mixed together, that's a buffer. And we can use the Henderson-Hasselbalch equation following the equation that's given there. The next column is strong acid only, those 7 strong acids. We know that their molarity, or at least all of them but H2SO4, their molarities are equal to H3O+, so we can calculate the pH that way. And the 8 strong bases, we know we can calculate their pH. I know I only have POH written there, but you could also, then you can convert that to pH. We know that the 5 strong bases with 1 hydroxide, their molarity is equal to the hydroxide. The 3 strong bases with 2 hydroxides, we take their molarity times 2, and that's equal to hydroxide, and then we get the pH from that. So Chapter 17 isn't only acid-base stuff, but the majority of what we have left are to look at the other 3 boxes here. The one that says strong acid and strong base, and then weak acid and strong base, and weak base and strong acid. The reminder equations, man, words are tough, are most of these equations we've seen before. A couple of them are new, but those are just helpful hints. Then down there at the bottom it says strong acid and weak acid, strong base and weak base, and then at the equivalence point of the titration. So we're going to look at all those things, but that's what Chapter 17 is. So my very strong suggestion is pause the video right now and either go to Canvas and open up this file, which is called Summary of Solving Acid-Base Calculations. That's the name of the file in the Chapter 17 folder. Open it up and just have it there so you can refer to it, or even better, if the option is available, print it so then you can refer to this. Because if during lecture I would have been pointing at this a lot, we would have been referring back to this table. I'm still going to refer to it, it's just I'm not going to be able to, I'm not going to be able to use my finger to point at it because that's not an option. I'm going to go back to our lecture and we're going to pick up here. So we're going to be focusing on the box on that table that says strong acid and strong base. So the good news is you guys have already done an acid-base titration using a pH meter, so you know how this works. This picture, my favorite part of the whole picture is that the pH meter is floating, which was not our experience. So you guys did this lab right before spring break. And you did the 1 milliliter increments or the 0.1 milliliter increments. So you've experienced that. Ideally, we would have done a second one with a weak base and a strong acid, but either way, you've experienced it. So what these calculations that we're going to be doing are, it's picking a point during that titration. So after adding 17 milliliters. If we were in the lab, we could add 17 milliliters and measure what the pH is. But number one, we're not in the lab right now. But number two, it's not always feasible to be in the lab. So the calculations we're going to learn are how can I calculate what the pH would be at 17 milliliters into the titration. So these are calculating what the pH would be based on the information that we have. So that's what we're going to be looking at. Okay, so a reminder of some terminology. The term equivalence point is when the stoichiometric amount of acid is equal to that of the base. When we did our titration with the indicator, that was when the light pink color actually showed up at the end point, which was 1 drop past the equivalence point. But when we did our pH meter titration, the big jump happened at the equivalence point. So we're going to be comparing things to the equivalence point. So just a reminder, equivalence point, when the moles of acid are stoichiometrically equal to the moles of base, it's when the big jump happens or the big drop happens, depending on the chemicals that you're mixing together, or pretty much when the indicator changes color. Okay, so we're going to talk about titrations with strong acids and strong bases. So we're going to do several different calculations. So this picture here is just the titration curve. So you're going to be making titration curves for the weak acid and the weak base labs that look like this, or similar to this anyway. This is just tracking what the pH was based on the amount of how many milliliters of, in this case, sodium hydroxide or whatever chemical was in the burette. So just keeping track of that. And so these calculations, it's just going to be picking points along this titration curve and calculating it. Just in real life, you're not going to have a titration curve in front of you to look at, to figure out what the pH is. That's why we're going to learn to calculate it. So for this section, this video, we're going to do 3 calculations. It's pointing to 4 different spots. We're not going to do the first one, which was how to calculate the pH if you just have a strong acid, since we learned how to do that in chapter 16. So we're not going to do that one. We're going to do, once I've mixed them together, but before the jump has happened, at the equivalence point, and then after the jump. Now, as we go through the math, other than at the equivalence point, it doesn't actually matter if you know where along this titration curve the calculation is. So I'll hopefully try to explain that as we go through this. So here is where I would like you to grab that handout with the weak acid only, weak base only, strong acid only, those things on it. So as we do calculations in chapter 17, again, I want you to read the question, identify what type of chemical each chemical is, which could be strong acid or strong base or weak acid or weak base. I added neutral as an option, but in real life the questions aren't going to have neutral things, but sometimes our products are. So once you've identified if it's each chemical, if it's strong acid, strong base, weak acid, weak base, then you can refer back to the handout to see what the heck should you do once you've done that. So let's start there. Let's look at the chemicals in this question. Oops. Boop. Okay. And no. Why can't I use my pen? There we go. Green. Okay. Look at the questions in the chemicals in the question and identify them in those categories. So I'm ignoring the numbers right now. So I'm looking at the first chemical, HBr. Hopefully we remember that's one of the 7 strong acids. So I'm going to write SA, strong acid, right above it. Skip the numbers, go down to NaOH. Well, that's one of the 8 strong bases. So I'm going to write SB right there. So at this point, we still aren't even really looking at the numbers, but we're recognizing we have a strong acid and a strong base. So I can go look at that chart where it says strong acid and strong base. It's in the second column, 3rd box down. And what it has in there is a list of steps. So we're going to follow those steps. That's what we're going to be practicing here. Step number 1, once we recognize we have a strong acid and a strong base, it says write the balanced equation. So you are going to have to remember some stuff from Gen Chem 1. We're going to take those 2 chemicals and write them as the reactants, and then we're going to have to predict the products before we can start doing our math. So HBr plus NaOH arrow. This is not an equilibrium arrow. Strong acids and strong bases do not go to equilibrium. So to predict our products, this is an acid-base reaction, which is wonderful and everything, but more importantly, it's a metathesis, or a double replacement reaction, which means this thing is going to go with this thing is going to go with this thing. Okay, so H and OH are going to come together and be H2O. Na plus and Br minus are going to come together to make NaBr. We've double-checked this is balanced, and it is. So that's wonderful. Okay, so now I want us to label, again, what type of chemicals we have. So HBr, I'm just going to write SA for strong acid. NaOH, I'm going to write SB for strong base. H2O is neutral, so I'm going to write an X there. Then NABR, when we look at that, it doesn't immediately jump out as, well, it's definitely not one of the 7 strong acids or one of the 8 strong bases. It doesn't look like a weak acid. And so normally our default is, oh, well, then it's a weak base. Well, the issue is this is an ionic compound. And at the end of chapter 16, we learned how to identify ionic compounds as acids, bases, or neutral, following the rules of positive charges are acids, except for the list of exceptions. Negative charges are bases, except for the list of exceptions. So that's what we're going to have to do here. It's an ionic compound. So when we predict our products, almost every time, one of them is going to be water, which is going to be neutral. The other one is going to be an ionic compound. So in order to figure out what it is in terms of acid, base, neutral, we're going to have to follow those rules. So thinking about this, sodium is a positive charge. Positive charges are acids, except for that list of exceptions. The list of exceptions were the positive charges that are part of the 8 strong bases, which sodium is. So I'm going to write an X above that because it's not an acid. Br minus, well, it's a negative charge. Negative charges are bases, except for the list of exceptions, which are the negative charges part of the 7 strong acids, which bromine is. So that's neutral. So both water and sodium bromide are neutral. Once we've written our balanced equation, it doesn't say this on there. But again, I want you to write the type of chemical above every chemical. If it's neutral, the good news is we get to ignore it. So I'm just going to draw a line for both of them because we are done with them. So now we're going to go on to step number 2, which says convert to moles of each chemical. All right, now it's time to look at the numbers. So looking back at the question, we have 4.50 milliliters of a 0.1000 molarity HBr. So I'm going to start by just writing these numbers down. 4.50 milliliters of a 0.1000 molarity. We have 50.00 milliliters of a 0.02000 molarity. So we wrote down numbers. What number 2 again said, convert to moles of each chemical. Well, none of these numbers are in moles. So we're going to have to use what we know about molarity. Just moles of solute over liters. To take the milliliters and the molarity and convert them to moles. Our textbook super likes to use millimoles, which is just leaving the volume in milliliters and plugging that in the liters spot. And then when you solve for moles, you get millimoles. I don't know why, but I think millimoles are dumb. So I'm going to just do moles, convert my milliliters to liters, and then multiply that by the molarity to get moles. So when I did that, what we're going to be making here is a before and after table. We made this when we were doing the beginning of chapter 17. So the before row, I'm just taking my moles, 0.000450 moles. Again, those moles came from me using those 2 numbers. And then for the sodium hydroxide, I get 0.001000 moles. And again, that moles came from me using those 2 numbers. Okay, so that was step 2. It said convert to moles of each chemical. We did. Step 3, subtract the limiting reactant. So what we're doing is we're looking at those 2 moles. What's going to happen is these 2 chemicals are going to react with each other until the limiting reactant is gone. So to figure out which one is the limiting reactant, we're just going to look at the 2 number of moles and pick the smaller number. So the smaller number is 0.000450. So what I'm going to do, subtract limiting reactant, I'm going to take both number of moles and subtract 0.000450 moles. This one is 0.000450 moles. What's happening is, again, these 2 are reacting with each other until one of them is gone. And so both chemicals, we're going to see a decrease because they both are reacting. What we have left is the HBr is completely gone now. Sodium hydroxide, there's some left. The water and the sodium bromide we didn't care about because they're neutral. So what we have left at this point is just some sodium hydroxide left over. So that was step 3, subtract the limiting reactant. Okay, step 4, it says calculate the pH from the remaining strong acid or strong base after converting to molarity, and it refers you to the C strong acid only or strong base only. So what we have is, at the end of this question, the only chemical we have left is sodium hydroxide, which is a strong base. What we know about sodium hydroxide is it's one of the 8 strong bases, so its molarity is equal to the OH minus concentration. And if we know the OH minus concentration, we're able to solve for pH. The issue is right now, I don't have the molarity, I have moles. So we need to remember how molarity works. So I'm going to take 0.000550 moles, and we're going to have to divide that by liters. So moles of solute divided by liters of solution. Well, what's happening here is this is data from a titration question. So what's happening is the 50.00 milliliters of sodium hydroxide was in the beaker, and the 0.1 molarity hydrobromic acid was in the burette. And what they did was they just added HBr, and they stopped at 4.50 milliliters. And now we're supposed to figure out the pH. So when we do our titration, that 4.50 milliliters from the burette, wouldn't that fall into the beaker with the 50.00 milliliters of sodium hydroxide? Like when you added your chemicals with a burette, they mix together. So the volume here, it's the total volume because they've mixed together. So it's 54.50 milliliters, which is 0.05450 liters. So I can grab my calculator and do the math here. I'm not going to round yet because I'm still not completely finished with the question. 0.0109174 is the molarity. Okay. So that's still not my answer. The question asked for the pH, but I know that that's the OH minus molarity. So what I'm going to do now is I'm just going to take that number. I know I switched slides, but it's the same question. I'm just going to go back to OH minus is equal to 0.0109174 molarity. And what we need to do is try to solve for the pH from that. So it referred us to go look at the strong base only thing. So what we're going to do is I'm going to use this hydroxide molarity. The way I like to do it is I'm going to convert to the POH and then subtract it from 14 to get to the pH. So what I'm going to do is solve for the POH by taking the negative log of the OH minus. So the negative log of that number, which 3 sig figs is going to get me 3 decimal places. So I would get 1.996. So the POH is 1.996. The question asks for the pH though. So I'm going to use this equation, substitute the POH into there, and my pH value is 12.0004. So I just solved for the pH at that time. Yay, that was fun, right? We followed our steps, and we used stuff that we learned last chapter. Okay, so we're going to keep trucking on this. Good or bad, the post-lab questions for the weak acid, like the pH meter titration and the weak base titration, those are going to be lots of good practice for this. So now we're going to move on to a different question. So it says at the equivalence point. This is when the jump would have happened. So at the equivalence point, the only thing that's going to be left, the issue is at the equivalence point, both the moles of acid and the moles of base are gone because they're both the limiting reactant. That's when the moles are equal. So their moles are equal. So they're both gone. All that's left is the water and the sodium bromide. So that means that the pH is 7 because all that's left is neutral stuff. Okay, so if a strong acid and a strong base are mixed together at the equivalence point, the pH is always 7. That's an always thing. Okay, and it actually says that on our little sheet. It says at the equivalence point of titration, there's a strong acid and a strong base, and below that it says pH equals 7. So always at the equivalence point of a strong acid and a strong base, the pH is 7. So I could ask that question. You don't have to do any math. You can just say 7. The question that I'm going to ask that will require some math is what volume of, well, so pretty much it's going to be how much do I need to add to get to the equivalence point. Okay. So what volume of 0.1000 molarity HBr, which is a strong acid, must be added to reach the equivalence point, which is an important set of words right there, with 50 milliliters of NaOH, which is a strong base. Okay, so at the equivalence point, and this is something I should have written down on that chart, but I don't have written down, so I'm asking you to add that. At the equivalence point, we can use the M1V1 equals M2V2 equation. For acid and base. This is assuming a 1-to-1 mole ratio. Okay, if it's not a 1-to-1 mole ratio, we'll have to take into account, the mole ratio. But at the equivalence point is the only time we can do this. This was true in our weak base, and it's going to be true in our weak acid and weak base lab when we had to solve for the molarity of the weak acid or the weak base. we use this equation. So in this question, we're just solving for the volume, the V, of the acid. So I'm just going to take the three numbers given in the question and plop them in here. The molarity of the acid is 0.1000 molarity. Volume of the acid, I don't know. Molarity of the base, 0.02000 molarity. Milliliter, or volume of the base, 50.00 milliliters. So I'm just going to do my math. And I end up V1, my calculator just says 10, but because of significant figures, I'm going to say 10.00 milliliters. So they would have seen the big jump happen at 10 milliliters. Okay. If I had asked the question, what is the pH at the equivalence point? If it's a strong acid and a strong base, the answer is 7. If I ask how much of one chemical will there be, or what will the molarity be at the equivalence point if these things are true? At the equivalence point, we can always do this. So again, I would write that down on that chart. Because that's true if it's a strong acid and a strong base, or a weak acid and a strong base. It doesn't matter. Just acid equals base at the equivalence point. Okay, so we're going to do one more calculation. Same titration. We're just picking different numbers. So at the top of the page, it says after the equivalence point. In real life, at the end of the day, I don't care if it's after the equivalence point or if it's before the equivalence point. So that's just me telling you that, but you don't need to know that to solve this problem. The only time that is special is at the equivalence point. If it is at the equivalence point, we can do M1V1 equals M2V2, and for a strong acid and a strong base, the pH is 7. Okay. But any other time, if it's not at the equivalence point, I don't care. We follow the steps on the chart. So again, I know it's the same chemicals, but if I were reading this question, I would first want to look at each chemical and identify the chemical as a strong acid, a strong base, a weak acid, or a weak base. So HBr, strong acid, and AOH, strong base. So in the question, we have a strong acid and a strong base. So I'm going to go look at my chart where it says strong acid and strong base and follow the steps. It says first to write the balanced equation. So it's actually going to be the same equation as before because it's the same two chemicals. So I'm going to be lazy and label it green. Strong acid, strong base, neutral, neutral. Okay, and if you go back, you can see why I said sodium bromide was neutral. Since these are neutral, I'm going to go ahead and cross them out. So that was step 1. Step 2 says to convert to moles of each chemical. So I'm just making myself a label that says before. So for HBr, I have 12.76 milliliters of a 0.1000 molarity solution. For NaOH, I have 50.00 milliliters of a 0.02000 molarity solution. None of those are in moles, so I'm going to convert them to moles. So when I do that, I get 0.001276 moles of HBr and 0.001000 moles of NaOH. That was step 2, convert to moles. Step 3, again, I'm looking at the table, the chart that I gave you. It's called Summary of Solving Acid-Base Calculations. That's the steps that I'm following. So step 3 says subtract the limiting reactant. So we're looking at our two reactants, HBr and NaOH, and choosing our limiting one by looking at the number of moles, picking the smaller number. So this time, 0.001000 is my smaller number. So I'm going to subtract that amount from both sets, minus 0.001000 moles. So this one's going to be 0. This one's not. 0.000276 moles. So at the end of the reaction, sodium hydroxide's gone. Okay. HBr, we still have HBr left over. So we have to solve for the pH based on the HBr information. So since HBr is a strong acid, we can look back to our strong acid only chart and see, well, the strong acids, including HBr, its molarity is equal to H3O+. If we know the molarity of H3O+, we can solve for the pH. The unfortunate part is we don't currently know the molarity of HBr. We know how many moles of HBr, so we are going to have to solve for that. So I'm taking the moles of HBr, and I want to divide it by the volume. Again, this is a titration, so when we do this titration, the volumes are going to add together. So my volume that I use here is going to be 62.76 milliliters. I took the 50 and the 12, and I added them together. And that's going to give me my molarity of H3O+, which is equal to 0.004397706. I didn't round because this is still not my answer. So this is not a pH, this is a molarity. So I still have to get to pH. So again, I ran out of space. So next slide, same problem. I'm just going to rewrite, come back, that HBr, the molarity of HBr is equal to the molarity of H3O plus, which is equal to 0.000276 moles divided by 0.06276 liters, which is equal to 0.004397706 molarity. So this has 3 sig figs. So I know that H3O plus is equal to that. Well, pH is the negative log of the H3O plus. So I just need to take the negative log of 0.004397706. This has 3 sig figs. So my answer is going to have 3 decimal places. So when I did that math, I got, come back, 2.357. So that would be my pH at this point in the titration curve. So again, just one quick reminder, that chart that tells you, that I keep referencing, the summary of solving acid-base calculations, that really is your friend right now. And when you read a question, the most important thing are what type of chemical are they? We don't actually care if it's before or after the equivalence point. That doesn't super matter. The only times we're looking for is at the equivalence point is handled special, but otherwise, meh. So we just watched a whole, like 20-something minute video about strong acids and strong bases. So our next video is going to go through the weak acid and strong base scenario.